In this separations video, I'll explore the assumption of equilibrium stages in much more detail. Remember that this is one of the key assumptions that we're making when we do McCabe-Thiele analysis, that exiting streams are going to be in vapor-liquid equilibrium. However, as the videos that I showed last time hopefully demonstrated, this may or may not be true. So the first question that we might ask is this a good assumption? And if not, what happens if I don't have equilibrium? So first, in order to understand what equilibrium is, first have to understand what's actually going on when vapor contacts liquid in a distillation column. So here's a cartoon of that I just drew. So vapor bubbles are contacting the surrounding liquid, and this interface between the bubble and the surrounding liquid is what mass is transferring into or out of. So stuff is evaporating from the liquid phase to go to the vapor phase, and stuff is also condensing to go back from the vapor phase down to the liquid phase. So in order for these two things to actually reach equilibrium, I need sufficient surface area, and I'm talking about surface area of vapor bubbles to the surrounding liquid. And I also have to have sufficient time. I have to have this vapor and this liquid contacting each other long enough for equilibrium to occur. Now, how long does equilibrium actually take to occur? That's something that you might be able to determine experimentally, but oftentimes we don't have a really good estimate for that. So you may want to overestimate, but then there's no real good way to control that either. So instead of having an equation that accounts for the surface area and time in a lot of detail, how it's usually accounted for in practice is with the concept of a Murphree vapor efficiency. So the vapor efficiency has a variable name E sub mv, and it quantifies deviations from equilibrium. So in this formula, Y sub n is the actual composition of vapor leaving stage n. Yn plus 1 is the actual composition of vapor coming in from stage n plus 1. So remember, this is the stage below. And then finally, this Yn star is the composition of vapor that would be in equilibrium with the liquid leaving stage n. So by breaking this equation down a little bit, you can easily see that if Y sub n is equal to Yn star, if Yn is equal to Yn star, that means that the actual composition of vapor leaving stage n is equal to the composition of vapor that would theoretically be in equilibrium. And if this happens, then E sub mv is equal to 1 or 100%. So that means I have a perfectly efficient equilibrium tray if my vapor is actually getting to the theoretical equilibrium that I have. So how does this help you in practice? So what you can do with this EMV equation is rearrange it to solve for Y sub n. So if I rearrange this Murphree vapor efficiency equation, I can obtain Y of n is equal to EMV times Yn star minus Y sub n plus 1 plus Y sub n plus 1. And now this is an equation for Y in terms of Y star, right? So it kind of starts to resemble a straight line. Well, not a straight line, but you can derive it by knowing what Y of n star is. So I can substitute that. Remember, Yn is equal to EMV. And then for Yn star, you can substitute alpha xn over 1 plus alpha minus 1 xn. Right, and these are all things that you would theoretically know. The last thing you'd have to do is to estimate what this EMV is. So in practice, if EMV is a number, say it's 50%, so say this is 0.50, then you could plot what the actual equilibrium curve would look like. So I'll show you what that looks like. So on our typical YX diagram, or this is strictly for the equilibrium, let's say I have an equilibrium curve that looks like so. So it looks just like it usually does. Equilibrium curve. And you could plot this just by choosing a range of xn, so 0, 0.01, 0.02, so on and so forth, all the way down to 1. And you could then plot what Y of n star would be. And this would be the alpha equation. So you'd have to know what alpha is. Right, now by knowing what these two are, I can then plot yn with the equation that I just wrote above. Right, the only thing I would need to know now is what EMV is. So I can use all these y sub n plus 1s from, actually, sorry, I forgot about one thing. You also have to plot what y of n plus 1 is. And to do this, you also need to know what the material balance would be. So you'd have to plot the operating lines, right? But that would be a function of xn, and if you define xn, the range of xn, then you can calculate what y of n plus 1 would be. And then from there, all you need to know is what the EMV is, and then you'd plug this Murphree vapor efficiency curve into there. What would actually end up happening is you would sketch in this equilibrium curve, and what I'm plotting now in green would be called the pseudo-equilibrium curve. And it should be a little bit inside what the actual equilibrium curve is. And that would make sense, right? Because if your plates aren't as efficient as you hope that they are, then it's going to have the same functionality as reducing that relative volatility a little bit. It's called pseudo-equilibrium curve. Okay, so when you plot your operating lines now and you start stepping stages, the only difference that you would have to make, and the change would be, instead of stepping off of the equilibrium line, you're stepping off the pseudo-equilibrium line. And once again, hopefully, as I've shown you, and you can kind of envision for yourself, if the equilibrium curve is in a little bit from what the actual equilibrium curve is, you're going to need more stages, which again makes more sense in the context that a stage is oftentimes not in equilibrium and therefore not as efficient as an idealized stage. So that'll wrap it up for this video. Got one more video coming up for today.